ladies and gentlemen, let me tell you, it's a great pleasure to be able to speak to you this afternoon and to attempt to show you, to distill into 1 hour of talking to you what's taken me pretty much a maximum amount of my lifetime to work out. You can get there more quickly because I can try and distill it. So we have STRAM. We've got a lot of information that comes at us from buildings and goes to the web. And we can address the web from anywhere at all in the world. And in fact, I'll give you a live demonstration a little bit later on of data coming in to here from New York City and right up to date. We look at all sorts of structures. And I've got examples here of a few. This one here on the left, bottom left, that's in New Zealand. We've got the center bottom is a structure, a church-type structure in New York State, in the United States. And on the bottom right is the Corbin building in New York City, very close to the site of the World Trade Center towers that came down on 9/11. Because of that, they built a new subground pedestrian area, which is a transit center. It links up various different transit systems in New York City. But what happened here was, to do that, they created a hole at the side and then filled it out with a new shopping center. The Corbin building on the north side had a 9-story brick wall, and people were very worried about the stability of that. The conventional approach was to look at the tilt of that wall and see what was happening to it. We went through a number of meetings in which the first one said, well, we've reached the limit that we've set for tilt. What do we do now? And of course, the obvious solution is increase the limit. So they increased the limit, and it got to that one as well. What do we do now? Well, we went around the table, and people were saying, yes, we've got this, don't know what to do. Yes, we've got this, don't know what to do. And then it came to us in STRAM, and we said, well, we can see the tilt that other people are monitoring, but we are also looking at the holistic behavior of the entire structure. And we can tell you that all of these limits that you've passed have made no difference whatsoever to the holistic behavior. Not quite no difference whatsoever. There are small changes during a day because of the temperature, because of the traffic, the excitation, all sorts of things like that. All those normal variations were not changing. So we were able to say to them, continue doing what you're doing and you won't have a problem. So the next meeting that occurred, when they reached a new limit, they wanted to hear from us, first of all, because they wanted to hear about that holistic behavior. That saved the MTA, the Transit Authority of New York City, $150,000 a day, because they didn't have to stop work. And it's that sort of thing that I want to impress on you is possible using the technology that we've developed, because it gives you a management tool to enable you to make instant decisions about what's going on and have a very high degree of confidence in what you're going to do. Now, I said we look at different buildings. These 3 buildings are also from New York City, and bottom left we've got a 20-story condo building, and they are constructing 2nd Avenue subway just outside, boring down underneath the building and then going through a right angle down through a tunnel to create a new subway station. Clearly, we want to know what the effect on this building is. So we were monitoring, and we've been monitoring for 2 years there, looking at the changes in the structure, checking on actually a load transfer. Because if you build a tunnel underneath a structure and you go through its foundations, you want to make sure that you've taken the loads of the building and transferred them to another path. So we were monitoring all through that. and it's been very successful. We had a surprise though, because we did pick up an instability, but it was a totally unexpected one. It was a panel on this face down here which had come loose, and probably because we had a very hot summer this last summer. It's the northern hemisphere, so it's the opposite of here. And that was a single panel which was flapping around. It had come unstuck from the structure itself. And that signal, because of a potential failure of a single panel, had come through to positions up here and over here, quite some distance away from where the problem was. Now we are looking at vibrations in the structure, and we're drawing conclusions about what's going on. So the vibrations do transmit through the structure. And you can see from this example, quite some distance, we were measuring the effects of that delamination. Center bottom picture is Fifth Avenue in New York City. In this particular case, no diagrams, no plans of that building were available. And yet the owners wanted to add 3 stories. How are you going to do that? What you do is you calibrate using our methodology. You calibrate a mathematical model. Take that to the buildings department who are happy with the methodology, and you then look at where the differences from expectation are. We found some stiffness deficiencies around 3rd, 4th floor of the structure. Put that right, alter that in the finite element model, and look at the response, and then it's okay to add some extra stories on the top. Foundations, that's a complex question in New York City, but our accelerometers are triaxial. So what we are looking at is both the X and the Y direction and the vertical. Now, the vertical response, dynamic response of the structure is a function of effectively the building sitting on a spring. For those of you who are geotechnical engineers, you will look at the characteristics of the soil, integrate all your information, and calculate a spring constant for the structure. You may distribute it. We can't do that, but we'll take an average value underneath the structure itself. So in that case, what we've got is a look at that soil spring constant averaged underneath the structure. Looking at this 3rd building, there is blasting going on across the road. New York City allows you to construct underground and make big caverns by blasting away. Quite naturally, people who are nearby are concerned at what might happen to their structure. And in this case, we were monitoring, again, for a period of about 2 years there. And we monitored the effects of the blasting, the intensity of the vibrations, and the effect on the building. And we're okay going through there. Okay. We look at various different types of structure. For instance, bridges, dams, tall buildings, towers, stadia, and waterfront and offshore structures. The point about this is that the technology treats a structure as a system. And we can treat any structure which can be defined as a system. In other words, it has boundaries. It has edges that are well defined. If we don't have that, then we can't use the technology that I'm talking about here. Like, for instance, tunnels or pipes. Then effectively all you've got is an infinite half space outside the structure. Dams, some of the structures that we've tested here, Emerson, top left in Switzerland, is 200 meters tall, and it's 2,000 meters up in the Alps. This was the very first time that we had shaken a full-scale dam of this size and calibrated what the normal modes of vibration are for such a structure. That remains one of a series of large-scale tests of dams conducted throughout the world. Other people have done just individual tests under controlled conditions. We shook 12 separate dams of various different types. So Contra Dam here is also in southern Switzerland, but this is in Ticino. And the picture there is taken after a storm one night in which the reservoir level rose by 10 meters and it overtopped the dam by 2 meters. Standing on top of that, the morning after it happened, was a salutary experience. That was shaking and it felt dangerous. It survived. Wimbledon Dam is a buttress dam. That means that we have a series of buttresses, and between these buttresses are expansion joints. That sounds fine, except that it leads to very complex behavior. If the reservoir level is high, then the whole thing acts as a monolith. If the reservoir level goes low, then each of those buttresses acts as an independent structure with a minimum of contact with the adjacent member. So what we were doing, shaking the structure, was very interesting, because one of the things that we do is to shake at a resonance and then suddenly stop the vibrators and look at where the energy goes. And you could see waves of energy as we were measuring across different buttresses. You could see that energy being transferred across the dam from buttress to buttress. Unexpected behavior, unless you actually know that that's the sort of thing that you really would expect. Next thing, and again, it's sort of unexpected. Many people say, well, can you do earthen dams? And yes, we can. We shake them, we shook them. Nowadays, we don't need to shake our structures because we've got the calibration from these induced vibration tests. We know what normal behavior is from this. So earthen dams, yes, they're fine. Clay core, large amount of berms down here. We've got top left, Lower Glendevon Dam in Scotland. And if you look carefully, you can see that the coping stones along the crest have been forced by the valley sides moving in towards the center. They've raised in the middle there. So we looked at the behavior of that dam and found that there was a weakness in the middle. But that would not be important if we lowered the reservoir level, and in fact not by an enormous amount. And that continued to be the case. There's a swarm of very minor earthquakes underneath that reservoir. Briani Dam, there was no real problem with it. We shook it, we got the characteristics, and it emphasized that the sorts of things that we've got from earthen dams are general. You can take it from one dam to another. So now, we don't have to use a vibrator system to shake a dam. We can use ambient excitation. And in fact, we use that for all of the structures that we've got. Because we've done these calibration exercises, and we've looked at what the normal behavior of a structure is. Various different types. Tall buildings, dams, cooling towers, chimneys, offshore structures. We've looked at them all. We've got the normal sort of behavior. And I'm going to come into a little bit more detail, because what is normal? And as a matter of fact, normal all the way around the world is the same. It might be that the design makes designers do something slightly different, but the normal deflected form of the structure is really very well defined and can be retrieved from the response to random excitation, such as wind, wave, traffic, or earthquake, of course. We looked at big bridges. We've looked at the Manhattan Bridge and the Triborough Bridge, as it was called. It's now the RFK Bridge. And again, we've found all sorts of things with our ability to measure very, very precisely and down at low amplitude. What we've got here is aerodynamic instabilities that occur on a large span bridge. And a period, a natural period of shaking of the center span of the RFK bridge of 10 seconds. 1 cycle every 10 seconds. Now, it's difficult to measure at such a low frequency, but we've done it. We've retrieved not just the frequency, the period, from that structure, but also the damping and the interaction of the structure with the wind, so that we avoid the problem of the Tacoma Narrows type effect. These are the sorts of buildings, structures that we can look at, buildings, transportation, railway and road bridges, for energy, dams, wind turbines we've had a look at, to hydroelectric effects, hyperbolic cooling towers, and transmission towers. And then marine, mooring, berthing, the dolphins, offshore platforms, docks, piers, jetties, all of these we've had a look at, and we've got information coming off their behavior. We like to have this analogy, an SKG analogy. I'm sorry, here it should be SCG, and it's structural cardiogram. We actually have that name trademarked, and the idea is that it's analogous to what you do with your cardiologist doctor. You go to have some electrodes placed on you. You may do a stress test or something like that. But those transducers will collect the data and will send them off to a cardiologist, an expert. We do the same thing. We'll put transducers onto a structure, collect the data, and then an expert will look at those. The analysis depends on the skill of the expert and the interaction with the client. What do they want to do? What's possible? And where do you go with this? So the question here is, are those data of good quality? We have good quality data using the most precise accelerometers that are available on the market at the moment. We're always watching that just to see what changes there are. So first off then, let me go into a little bit more detail about what we do and how we do it. The first thing is that statics, the sort of thing that we're all brought up on in university. We look at a force or a load acting on a structure, and we look at the deflections, the moments, various things like that. But if you take a more general equation and you set the frequency to 0, then those dynamics equations will lead you into the static equations. If you set the frequency to resonance, then you get the classic equations of the response of using structural dynamics. The most naturally occurring forces that act on structures are random functions, like, for instance, the wind, waves, traffic, earthquakes, and we have to go to quite some lengths to make sure that we reduce all of those actions to something that can be codified. I actually sit on AS/NZS 1170.2, but we look at the 0.0 general conditions, and we work with our colleagues on 0.5 as well, where the major input comes from New Zealand. But the analysis of the random data is incredibly important to get right. If you do get it right, and it's not a simple task, but if you do, then there's a lot of information that can come out of the response of structures to random actions. Let me take us right the way back to the beginning and say, let's start with Newton's second law of motion. Force equals mass times acceleration. The force is acting on a structure. Well, we can have the actions of natural events, wind, earthquake, traffic, for instance. And what we say is we've got elastic forces opposing the motion, and we've got a damping force opposing the motion. So we've got those forces which we can incorporate into our overall force. Now we start making some assumptions. And the first one is that stiffness is assumed to be proportional to displacement. I think we're probably okay with that. The next one is wrong. The next one says the damping force is assumed to be a function of velocity. That is, It's a viscous damper. It's like the sort of thing that you find on automobiles to prevent wheels from bouncing up and down. That's a viscous damper. Have a look around a building and see how many of those you can count. They don't exist. When the concept was introduced, the term used was equivalent viscous damping. In other words, people understood that this is incorrect, but it's a nicety mathematically. It's very convenient. And for a long time, that caused us all sorts of problems, and particularly between wind and earthquake engineers, because damping is different at different amplitudes. And if you assume that it ought to be the same, then you've got different values to use for wind engineering and for earthquake engineering. And of course, the two groups will face each other off and say, you just don't understand what we do. What we've done is to put a completely different model to damping, work it through, and re-arrive at the concept of equivalent viscous damping. But now, we're not putting car dampers into our buildings. What we are doing is assuming that the major contributor to energy dissipation, that's damping, is friction. And it occurs as friction between large elements of a structure inside the matrix of a material. And we use the entire science of fracture mechanics to look at what we expect from the behavior of all sorts of structures. Having done that, we have a model, a physical model of what goes on in structures. Now, this is not my work that created this. This came from Tom Wyatt and his team at Imperial College. They shook us by saying, we've done experiments on footbridges, and we've got this model which says everything is stick-slip behavior. When you get very large elements, then they come unstuck and they move and they slide against each other at very low amplitude. As you move up in amplitude, then smaller and smaller elements are contributing. If you like, cracks are elongating, they're dissipating energy, until you get to the point where the smallest of small are dissipating energy. And under those circumstances, what you have is really micro behavior. You have molecular behavior. How do I know this? Because we've taken samples out of a building in Hong Kong that was hit by a typhoon within a week of being constructed. And we looked at samples where the stresses were smaller and where they were larger, and we found chemical differences to the cement paste taken from the same site, same batches, and so we got differences in which the energy had appeared as changes to the chemistry of the cement. That was a surprise too. Now, if we, and I'm not going to belabor this point, but these equations of dynamics actually take us into a lot of detail that we can work with. We can play tunes on this. For a single mode of vibration, what we've actually got is a modal mass and an acceleration. We've got a modal damping, now equivalent viscous damping, and we've got velocity in there. We've got a modal stiffness, and we've got the modal forces. Modal, that means that we are dealing with a single resonance at a time. These equations apply to a whole series of resonances of a structure, and we can apply them. We can manipulate them and get more common parameters like the frequency, the inverse of the period. We can have the damping ratio, the modal mass, and of course the forces that are occurring. So what do we do with this? How do we actually use these equations in our assessment of structures? Well, first of all, we have to define mathematically. And then we can use that in various different ways. We can use it in terms of creating a mathematical model. Finite element models, for instance, used to be that we used finite difference models as well. But finite elements are now the theme that everybody likes. Or we can go to heuristics. the sort of heuristics that there are in codes of practice, because some people have taken all of that behavior of structures that they know about and they've created some rules of thumb, some guidelines for how to design. Every single new batch of codification, in my experience, and I've been on code committees in the UK, Europe, Hong Kong, Australia, and Brazil as well. Everybody calibrates them against the previous one, just to make sure that they're getting a result that they're comfortable with. So when we had factors of ignorance, uncertainty, that we would put safety factors in, then we probably had about 40% as safety factor. Now, what we do is we're risk-based. So we modify the amount of risk that we are prepared to take. And guess what that factor comes to? Actually, it's about 40%. And the reason is that it produces the sort of structure that we're comfortable with. The sort of structure that says, we're doing what we've done for a couple of thousand years, actually more like 5,000 years, that we know what's going on, we know how they behave, so long as we watch carefully. And our codification will help people to stick to what we're comfortable with. Now, things do change. There are things that we do understand better. We get different materials. We are able to modify the way that we design with new abilities, like, for instance, computer-aided design. But if we're going to do that definition in the first place, we've got a number of things to define each mode of vibration, and they are these: frequencies of resonance, the force acting on the structure, that'll be in the code of practice. We've got the displacements or acceleration that are a function of the forcing function, mass and mass distribution in the structure. We've got damping associated with each of the resonances, and we've got the deflected form for the resonance. Deflected form, what we call the mode shape. So each resonance can be defined completely like that. The design condition is effectively the first mode of vibration, because that's the mode of vibration which reflects the quasi-static condition. So the frequency of resonance we can pick out with our technology by doing spectrum analysis. We do it correctly. We make sure that the variance errors associated with a random variable are reduced to levels that are acceptable. The force is defined by code. We actually say now to a designer, you choose the risk, and the code of practice will tell you what you do with the force associated with that risk. You can then apply that to a structure by creating base moments. We do that for both wind and earthquake engineering. And then we can look at criteria that tell us that the structure is okay. We'll look at stresses. We'll look to see that the response is within the elastic range, for instance, for human perception, that it'll survive a large earthquake, that sort of thing. We've got mass and mass distribution. Well, we can take that off design drawings. And then damping. Actually, you do a lot of testing of structures in laboratories at the design stage. Wind engineers will use a wind tunnel. Earthquake engineers will use a shake table and have a look for really big structures. And then we guess at damping. We guess. We put a value in that everybody thinks is okay. Well, let me tell you, it's not okay, and there are many errors associated with the values that people are taking. Now that, in AS/NZS 1170.5, leads you into these graphs where you make a choice of damping at 5%, 2%, whatever. But it's a nonlinear parameter. And I'm going to show you, it actually starts at a low value and works its way up to a high value. If you assume that at all amplitudes of response it's the same value, you actually get the wrong response. And that can be wrong by anything up to 100%, given the right circumstances, the right sort of phasing of the force that acts on the structure. So this nonlinear characteristic of damping is really important. It makes a very big difference to the real response of a structure. We still have all sorts of uncertainties and events that take us completely by surprise because we don't expect what happens to a structure. This nonlinear characteristic of damping is probably a very large factor in those surprises. Now, the other thing is, and something that we do, is that damping is so powerful as a parameter that we reverse engineer it. If we've got this mechanism coming from fracture mechanics, we can take those fracture mechanics equations to pieces and say, okay, now we are measuring the nonlinear damping characteristic of a structure, and it is telling us about the energy dissipation going on in that structure. It's telling us how it's occurring, what sort of dissipation, what sort of mechanism is causing that energy dissipation. If we take those equations and solve them, then what we've actually got is that the response equals force divided by stiffness for that static case. This is the laboratory test. We often do them on single beams, something like that. If we set the frequency to the resonance, then we've got response is the force divided by the stiffness, and then DMF, dynamic multiplication factor. That depends on the structure. So the dynamic magnification factor is a characteristic of the structure itself and the response in resonance. If the damping is small, DMF is larger. So dynamic equals static times dynamic magnification factor. And what we can do is say to everybody, okay, you can go back to college, you can use the techniques that you used, you can test by putting on a pushover force, for instance, and see what the structure does. And then if you've got a dynamically sensitive structure, or you've got a situation where dynamics is important, like earthquakes, take this dynamic magnification factor and you'll see what the response is. With the codes here, you'll do that through that choice of damping value. And I've already said there's a particular problem associated with that. So there's a confidence interval coming through right away. Now, the equation for the response during for a mode we'll call R. The mass is the force divided by the displacement, the damping, the frequency squared, and then a constant. Okay, that's solving those ordinary second-order differential equations at the frequency of resonance. That means that we can use it to calculate the modal mass. While we were shaking buildings, we knew precisely what the force was, because we had organized that with the vibrator system. We knew what the displacement was because we were measuring very precisely. And we knew what the damping was because we were measuring that very precisely in real time. This is from a real test on a real structure. So we've got different forces, Newton's peak to peak here. We've got the frequency varying with amplitude. We've got that amplitude there, differences from 0.65 up to 2.68 millimeters peak to peak. And then we measured damping. And in this case, it varied between 2.23 and 2.40. You take all those non-linearities, put them back into that equation, and calculate what the mass is, and you get something which is very consistent across all those amplitudes. So what we've done there is to calibrate that equation and show, yes, this is okay, it does work. It's not as precise as you might hope, but essentially it's working, and we know that it's working. So we can actually play tunes on this equation. We can use it differently, and that's part of our technology, because in assessing what a structure is doing, we will actually look at the risk that structure undergoes with different magnitude actions on it. And I'll come back to that in just a moment. This is what we do if we're calculating using finite elements or something like that. We actually use that second order differential equation, reduce it to mass times acceleration, and then stiffness times displacement, and say that the forces we can distribute against height. That's what we do with mathematical models. We'll reduce it to a matrix equation, which we can produce from finite element models. And essentially, it's saying that a force times the inverse of the stiffness matrix equals the displacement matrix. We look at that, that response, the displacement vector. And we look at that response and we'll see whether that is okay, will satisfy our criteria. But you see what we're doing, once again, we've got force times some sort of representation of the structure equals displacement. Now, if you're looking at the displacement response, there are many things that you can do with it. Instead of going to the force, looking at what the overall characteristics are going to be, whether they're going to be acceptable, what we'll do is take that displacement and see if it's acceptable. So we've got rules of thumb. In California, for instance, they say that the drift, the displacement, the relative displacement between floors of a structure must be within a certain limit. If we're talking about human perception of vibration, then we've actually got some other criteria that are used for whether people are going to feel comfortable. You don't want to be in your room, sitting down, watching a TV, and finding that the whole thing is moving around, coffee cups rattling or whatever. I'd like just to show you this transfer from the small to the large. We're familiar with stress-strain curves, and the rate of rise here is the E value of the material that we're looking at. We've got the yield stress, which occurs at some place, and the ultimate stress at another place. That curve takes us from the linear elastic range into the plastic range. Now, what we're saying is, let's limit ourselves to this area here, just below the beginning of the plastic zone. So what we're going to do is to say, now let us remove that and look at what happens with what we are doing. Now we are assessing the forces that come onto a structure in terms of modal forces, and we're looking at modal displacements. We have the same type of characteristic, but now we've got a modal stiffness for the structure. But that still defines this point before we move into the plastic range, which we can now use as a defining point. That's very close to what we use for human perception, human comfort anyway. So if we take a calibration at this point and we use our measurements of frequency and damping, and we compare what we're measuring of a structure as it is in the field, and then compare that with what the code of practice tells us it ought to be, then we've got that ratio between as is and as it should be if it's redesigned new. Okay, as it should be. That means that we've got to have predictors of what it should be for a structure in good condition. Now here, for a long time, we've had a problem, and that's why there's been this discussion between wind and earthquake engineers. First of all, measuring frequency, that's really quite simple. Expectation of frequency is really quite simple. It's fairly well defined by the geometry of a structure. It's not very much changed by the material. There are small differences between concrete and steel, but they're probably about 10%. Something that's used in California is to say the height of the building divided by 46 will be the natural frequency, inverse of the period, of a structure. 46.h, h being in meters, and that'll give it to you. Never mind the material, never mind anything else about the construction, just the height. Just the height. They use that in codification there. Next question, though, is what about damping? Now we've got to go away from this viscous damping model, use our equivalent viscous model, and then look at what that predicts for us. And there we've made an enormous breakthrough. Not only we have, but that's been repeated in Japan, and the Japanese are so keen on it that they've actually incorporated this into their code of practice by the AIJ, Architectural Institute of Japan, and the commentary on their codes tells you what to expect for damping values. And we use the equation like this. We are now looking at displacement per unit force. And look at what happens on the right-hand side of the equation. We've got 1 upon 8 zeta, f squared, m, and pi squared. If we're doing that for a building, the mass isn't going to change. It's not a rocket losing its mass. So all we've got on the right-hand side of the equation here is damping and frequency squared. By comparing x upon f at different times, or for different situations, we have a comparison. Let's take case 1, and we're taking measurements of damping and frequency off a building as it is. We've got the ratio of displacement per unit force. If we then look at the code and the expectations from the code of force and displacement. Now, displacement, which is expected, you can get from human comfort, from stress levels, or in some codes of practice, they'll tell you what the rules of thumb should be. Like, for instance, h upon 360, which appears in the ASC 7 code of practice, or pulled up by the code of practice, the international code in the US. But nevertheless, designers, and they're probably the same people all the way around the world, are using a heuristic to tell them what is acceptable, what sort of behavior is going to be acceptable. So we have to go on site and we will take measurements to retrieve that information. On the top left here is our SKG. This is a box which has been ruggedized. It's useful for use on site, and it allows somebody to go on site, connect accelerometers to it, and to make measurements over the required time. The required time depends on the random response of the building to excitation, and we can calculate that within 10 minutes of being on site. We'll know very quickly because we have a Wi-Fi connection. We can look at the response on our laptop or on our iPhone and see what's going on, what the frequency is, and knowing what sort of damping value we will want. That tells us what we need. This is a servo accelerometer. We currently use RefTech accelerometers, which are extremely precise. They actually give us an ability to resolve motion to better than the wavelength of visible light at 1 cycle per second. So we can monitor in great detail at low amplitude. We collect the data, we send to California, analyze, monitor. We can go back at regular intervals, or we can continuously monitor. This is a building on 2nd Avenue which had a big crack at the back of it. We monitored continuously for 2 years in positions up on the roof. Just 2 positions, because what we do is we go in and take a baseline. A baseline involves us saying, okay, we will measure in our reference positions, but we will take a traveler accelerometer and we'll put it in various different places in the structure, and we'll measure the vertical profile of displacement under random excitation. That's very successful. You don't need to monitor for so long when you've got a reference and a traveler, because you just compare the 2 signals and you look at the ratio and the phase between them. This is what I'm talking about here. What we've got is sway of a structure under a force, and we're doing spectrum analysis. So we've got frequency along here, which is the inverse of period. And we've got the amplitude on a logarithmic scale. This is from a real structure in the field. So we've got the frequency shown here, which represents this mode of vibration. And now we're measuring in this direction. Let's call it the east-west direction. And over here on this other spectrum, we've got a remnant of response, again at about 0.15 hertz. And in this case, that's because the mode of vibration isn't completely linear. There's just a little bit of twisting going on there. Look at what's happening in, let's call it the north-south mode across on the right of the screen here. Now we've got a mode of vibration measured in that direction, which is 0.25 hertz, and just a small remnant in the east-west direction there, which is just because there's not very much motion there. If we've got this middle one, torsion, then we're monitoring in both of those orthogonal directions. We are getting 0.4 hertz. So we can see that. Let me draw your attention, though, to the bottom left of this diagram where the building is swaying in the east-west direction. Let's just look at what's going on near the foundations here. And I'm going to move up in frequency and see more complex modes of vibration, and this is what we get. Okay? Looking at that bottom left side, we've got more motion at the foundation level of the structure. This actually says to us that the information carried by these different modes of vibration are different because they're sensitive to how much motion there is going on. If we've got more motion going on in the foundations here, we've got more information about that motion coming from that higher frequency mode of vibration. We can reverse engineer this. We can use the behavior in those higher frequency modes of vibration to look at what's happening in different places in the structure. It's like having a series of linear algebraic equations. The unknown is where you've got some damage, and if you have enough modes of vibration, you can actually localize where that damage is likely to be. It's only an indicator. It's not going to tell you precisely where it is, but what it does is gives you a management tool. We have a problem here. Go and look in this place, do a visual inspection, have a look and see what you can do with that. We also have here in this bottom spectrum a frequency around 0.9 hertz, which is splitting into two. It's no longer a single peak to that response. Now you may say, oh, that's just random variations, isn't it? You're not reflecting exactly what's going on. Those are random errors in the spectrum. They're not. In this case, the particular response repeated like that for a very long time. And we're very particular about how we do that sort of thing. So we've got differential influences from different places. This is a real response off a building on 2nd Avenue. We have the blue line as a baseline, and then spectra taken at different times, plotted on the same diagram. For the first, the fundamental mode of vibration, we've actually got a splitting up of the peak, and we've got a bifurcation occurring there. On the more complex mode of vibration, we've got an increase in the frequency. So in the first mode, we've got a decrease. In the second mode, we've got an increase. Why? Because in the first mode of vibration, we had damage in a facade on this building. The second mode of vibration, they'd actually built new foundations to the structure. They'd strengthened it up. So they made the foundation stiffer, and this more complex mode, which has more influence from the foundation, had increased in frequency. So there we've separated two things going on. Just two things in this case. But we've got a third one here. We've got this remnant peak at 1.29 hertz. We've actually got what is the beginning of a mode of failure on that structure. And in practice, what was going on here was that there was a big crack in a wall, which created that as well. Not large. This is 10 to the minus 9 G squared per hertz. It's small. It's not something that you'll see, but it's enough for us to keep an eye on it and make sure that it doesn't get too big. Information coming from this particular building. This building is a school building in the Bronx in New York, and it's actually got a railway line going underneath it. In this particular case, the green line over on the right is the expected mode shape, but we've got columns suspending the building above the railway. So we've got a lot of motion at first floor level, and then the sort of response that we expect. Now, 1.78 hertz is a sway mode of the building. We've got differences at third floor level between the north and the south of the building. That's an indication that we might have a soil structure problem. But look at what's happening in the vertical mode of vibration at 2.34 hertz. If we've got a structure which is on a soil and it is effectively moving up and down and forming a complete system with a mass spring coefficient to it, then we've got the spring constant of the soil. But the building itself ought to be going up and down monolithically. If that were the case, if that was happening, this green line is what we would measure at every single level in that structure. And look what's happening. There is more motion at some places than at others. What that means is that we've got, and in fact this is at the north end of the building, we've got the building concertinaing. The columns are not sufficient for the loads that they're asked to take there. They knew this at that stage. That's why we went in. And they put new shear walls in to try to negate this effect from the trains. Shear walls, the new shear walls cracked because they were not put in the position which would have been optimized to reduce this. If we'd been there beforehand, then we would have said to them, this is where you need to stiffen up the vertical response. Damping. We can get damping from half-power bandwidth, and that's essentially taking a spectrum and looking at the width of the spectral peak and then calculating damping from that. That is an averaged value. A lot of people use it, but I've said to you, it's important to understand that damping is nonlinear. So we use the random decrement signature, which grew out of the NASA Space Shuttle experiments early on. We have a three-part characteristic. We have low amplitude, increasing amplitude, and high amplitude. That is the norm for a building, a structure in good condition. Let me show you this, which is taken from a building in Hong Kong. The green line is the baseline taken averaged over a month. The yellow line is when an accident happened. They were boring a tunnel nearby and they had a collapse. The vibration level was so large that people ran out of the building in panic. We looked at it and we looked at the characteristic 1 month later and found that yes, there was damage that shook the building up and made things come apart, but they recuperated. They re-established themselves, but now the rate of rise of damping has changed and the overall capacity has reduced by 10%. But in those days, the code of practice in Hong Kong was so conservative that there was probably about an extra 20% capacity. So we went back to them and said, well, you're going to be able to withstand just a little bit less wind than you could before, but just repair the cosmetic damage and you will be all right. That's exactly what they did. So I've already covered this. Case 1 is measurement as is, and case 2 is the design of a new structure. When we actually put that equation to work and look at the relationship between case 1 and case 2, case 1 is what we're doing now, case 2 is what you would get if you design, then we can express that ratio in any way, including percentage of MBS. I guess I must have written this while I was watching TV in the United States. So, this is human perception of vibration. It was. Here we go. This is how people respond to vibration. So we've got characteristics here of human perception. This is the 1 percentile at the bottom, going up to the 99 percentile. Most of those red dots are taken from laboratory experiments. There's only been ever one full-scale experiment on site, this one here, and that lines up fairly well with what's going on in laboratories. So what that actually says is that we know what human perception of vibration is going to be. We generally design for 1 percentile so that people will not, under normal circumstances, experience vibrations that they don't like. I'm going to press on through here fairly quickly because we're running a little bit short on time. This was an experiment, this was a study of blasting near a church in New York State. We measured by acceleration 1.8 Gs peak to peak at 33 hertz, impinging on the structure. The waves came through the ground, and we had the Doppler effect because it wasn't straight onto the building. So we got slightly different frequencies at different places on the structure. 1.8 though, we looked at that, and we looked at the criteria required by law in New York State, and found that, well, it complied. It was okay. And then we looked at how the structure was going to really behave. This is just, by the way, at the same location, measuring by conventional means, and you can see this is using a device which operates on velocity. It gets the frequency wrong because of noise in the system. So it says that it's a much higher frequency, and that shifts all of these points of vibration intensity across to the right of the chart. If, and we had some instances where it was higher up here, again at the right of the chart, but if the frequency is taken back to what it really is, it can cross those thresholds. So the form of measurement is extremely important. These are criteria comparing human comfort with structural damage. Essentially, what we're saying is that by the time you get people inside a building panicking, they do not want to be there, they're running out, that's when you'll get light, cosmetic, structural damage. And you're still going up to higher values here. In fact, in the United States, we use, of course, the imperial system generally, and we say that these values are 0.5 inches per second, peak particle velocity. 2 inches per second is where you can say we will probably have the commencement of structural damage in unreinforced masonry. But at 5 inches per second, we're almost certain that we are going to have damage in a structure. So we've got this, we've got British standards, we've got ISO standards, we've got AS/NZS 1170, all have requirements for vibration intensity, which is likely to cause damage. The Germans in 1930 produced some criteria which are still very good, actually. Let me show you, though, and I'm going to press on over some of these examples. I'll come back to them if there are questions. This is the building that I'm talking about. The measurements using the conventional means were taken down here. We measured down there as well, but we also measured up at the top of the transepts and the nave and in the bell tower. These criteria say that that dynamic magnification factor will be a maximum of 4 in any structure, despite the fact that the experiments that produced these values were conducted in the 1970s with the equipment that was available and at frequencies that don't apply to structures such as this. So we looked at the relationship between these things. And we found this, measuring in different positions, a dynamic magnification factor of 10. Now, remember, we've got criteria that say 0.5 is what you aim for. 2, you might get damage, it's the threshold. 5 is certain damage. So 0.5 times 4 keeps it below 2, and everything is okay. But times 10, and you are up at the 5 inches per second value. That means you are almost certain to have damage. So we looked in detail at what was happening in the mode shapes and said the stresses are going to be greatest in between the transept, which is away from the measurements, from the blasting, that's over here, and the nave. So we predicted that there would be damage already caused in this area here. So they went and had a look and found new cracking as a result. This is an iconic building in the United States. It was the Army Corps of Engineers that were responsible for specifying how everything should go. We had raised an alarm. We'd saved them from a very embarrassing situation. Ladies and gentlemen, I'm going to come to a halt there with the presentation, but I would like just to show you, did right at the very start say, well, we can do these things and we can do them almost real time. And let me go back to this. I am on the internet at the moment, and what we have here is Stram Central. Now this is actually a signal which is coming off a building in New York City. It's on 12th Street, 438 East 12th Street. I've captured data over the last week or so. You can see nobody's working on site at the weekends, and we're up to New York City at the moment is just gone 11 o'clock, and we're at about 11 o'clock there. I can do all sorts of things with what is going on from what's here. We've got near real-time data. This is coming from the other side of the world. Let me come back to here and I'll show you what that response is right now. And I hope just before it changes past midnight, because the display is much better. Yes, there we go. So New York City is just gone 11 o'clock, and we've got data up to, well, it says 10 minutes to 11. In fact, the clock works away from real time after using for a long time. But you can see here, people arrived on site at 7 o'clock. They went home about 4:30. We'd got odd things which were going on during the day. And if we want to, we can actually convert that. I'm going to look at the now north-south direction because this will give you more information. This is the power spectral density. Look at this. We're on the other side of the world, and we can actually see what the response is, and particularly what the frequency content of that is. The blue line is a baseline, and then we're comparing with that at different times of the day. So as they arrive at work, then they start creating response. And we are at the end of this project now. There is an area where construction has occurred, and this particular building was not in a very good state, but the placing of a new building has added stiffness to it. It's also added mass, so the frequency has decreased, but effectively it's made it more stable. So we expect the frequency to go down there. And you can see the whole response is much cleaner, much better. So, ladies and gentlemen, thank you very much for your attention. I'm going to stop there and ask if there are any questions that anybody would like to have answered. We'll be very happy to address them. Thank you. From the point of view of engineering the structure, then it's often assumed that the interface between the structure and the ground is something that you can assume is okay. Somebody else is going to take care of that problem. But of course, with this vertical measurement, then we can see whether in general terms that's correct or not. We can't go into the detail that you'll get from the boring and the looking at the information that's occurring from those studies, but we'll get something which does correlate with the overall results that you'll get from the geotechnical studies. The question is, how do we decide on the number of sensors that we need? And we don't seem to have a large number of sensors. How do we do that? Okay, that's the question. The basic idea here is that by using the baseline measurement, we are making a series of measurements all through the structure by taking our traveler accelerometer to those places. Once we've got that, we've got the relationship of any point in the structure with any other point. So if we are going to have changes to the structure, which we're looking for, we'll see that through the spectral content, through the damping content, and if we see a difference, we'll go back and we'll measure that again. But again, what we'll have is a reference and a traveler going to different places, because we'll be looking for stiffness anomalies in various different parts of the structure. So one of the things about this technology compared with others is that we don't need to have a very large number of transducers. That puts the cost up enormously if we're trying to do that, especially with very large structures, because to get down to very low frequencies, which is associated with very large structures, you've got to have a very expensive transducers. We're dealing with that sort of thing because these failure modes will occur at very low frequencies. They are nascent, we see them, but you've got to be able to measure at as low as 1 cycle every 20 seconds, a 20-second period. So to be able to do that, you've got to have good accelerometers. But you don't need many for continuous monitoring, because you're monitoring the holistic behavior. You're actually coming from the entire holistic behavior of the structure and working your way down into detail. So from a single point, we can get most of the information about the entire structure. Not all of it, but most of it. Certainly enough to ring an alarm when we've got a change that needs more attention. If we get one of those alarms coming up, then we want to know where to go to have a look in more detail. But one of the things that people have been doing in structural integrity monitoring, they've been doing that for a little while now, is trying to work out how to retrieve data from a lot of different measurements and find the one which has got the information which will tell them where a problem is. We look at the modal response because the modal response integrates everything happening in the structure and will reproduce it at a single point. So long as we've got the right information to noise ratio to allow us to determine what's going on, then that'll give us an indication at certain times that you've got to go in and get more detail. Depends on the size and complexity of a structure, but if it's an ordinary sized building, well, the one across the road from here, it's, I don't know, what's that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 stories tall. We would probably get that done in a day. It's actually a triangular sort of shape, so we'd need to make some measurement, possibly as much as going into the second day. But from the random process point of view, we can get all we need within a day. It depends how large. Anything up to 20 floors, then we'll take every single floor. If we're talking 60 to 90, something like that, then we will choose the floors where there are nodal points, where there's moving from one phase to another, goes through the neutral point. In other words, we'll take maybe every 4 floors at other levels, but in those critical points, we'll take every floor. Yeah, we're watching what's going on, the discussions that are going ahead with the New Zealand Society for Earthquake Engineering. We're watching that. The big thing for us is that coming into law appears to be this 1/3, 2/3 criterion. So we've got a methodology for looking directly at that ratio in a very short time. So we'll take these measurements, we'll make that assessment. We've just done that for a building in New Jersey, actually. Different criteria that we're looking at, but the percentage NBS actually comes out of that. And we've got a building there which is in the red zone. It's well below the 1/3 point. So yes, we're watching what happens with that. We like the 1/3, 2/3 rule. We think that's a very good one. 1/3 capacity, 2/3 capacity. The International Building Code, which is used in the United States, has followed your example, actually. It's got these criteria. If you're going to change the structure, you've got to make an assessment and compare with what the code would tell you. And it's about a 1/3 rule for pull it down or repair it. But there, they've got, if you do any changes to the structure whatsoever, you've got to bring it up to 100%. You've got to make it look like a new structure. How do we decide where we're going to make those measurements, especially where there is a more complex structure? Is that a fair summary of it? Look at, I'm going to go to an example here. This is a school in Texas. 10,000 square meters floor area there. They're looking at increasing the floor plan of the school. We went in, and you can see those blue dots. We took reference positions which were in the middle of the roof there, and then we went with travelers around to various different positions. How did we decide? This is the real question. How did we decide where to have a look at? Look at the mode shapes that we've got here. Now what we're doing is looking at, on the right-hand side here, there is basically a north-south mode of vibration, but with distortions. In the middle, we've got an east-west with distortions, and then a complex mode, which is actually the lowest frequency mode. Why did we decide on these? Well, what we actually do is we'll make these measurements, and we'll take places where we're visualizing in our minds, if you like, what the dynamic characteristics are going to be. And we're looking specifically at east, west, and north, south, but then torsional effects as well. How often do we need to measure? And we're only doing that across the roof here. So we've got a number of positions, 2, 4, 6, 8, 10, 12 positions. That was all we needed. Each one of those took 20 minutes. The reference accelerometers stayed there for an entire day. So the idea here is you have to take enough positions to be able to define what these mode shapes are going to be. And I guess what I would say to you is that think dynamic is one of our mantras. You know, imagine how that structure is going to vibrate, and imagine how many positions you're going to have to resolve to be able to get that. We work directly with the people who are going to make the measurements, and we look at that and make sure that they actually get that right. But additionally, while I'm on this, look at this. In this particular case, we were measuring vertical vibrations as well as the X and Y, and we found 3 positions around their auditorium where the vertical response was larger. So we reported this. We didn't know why, but we said we've got 3 areas here which we've fingered. We're saying something's going on here. And they said, oh, we wondered if there would be something because we had timber piling underneath here, and then we had flooding, and we were worried that perhaps it had degraded. We said, okay. What they were going to do was to take borings all the way around that entire structure. And we said to them, have a look at these places first, because we're pretty sure that you'll find the cause of what you're worried about right off. And then if you want to spend more money, well, go ahead and do the rest of it. So the answer to your question is, it depends. And we will decide on the basis of our experience with other structures. As you can see, this one is an unusual shape, and we are looking at distortions that are occurring near the corners of a structure, yeah, that sort of thing. Additionally, if you are worried about how you deal with a structure after an earthquake, you haven't got to wait for another earthquake to come along. You've got this baseline taken at low amplitude. The earthquake comes along, the building changes. You have a look at it again, either sequentially, so you take another set of measurements, or if you're continuous monitoring, you can see it immediately. But that tells you whether you're okay or not, whether there have been changes. It gives you a new risk profile under the new circumstances. And then, if you have an aftershock, what do? You have another look at it, and you can see what's going. But you compare with the baseline. If you see differences from that, then something in the structure has changed. And that'll give you clues about what has changed and where to look for more detail. But the overall risk is something that, because of the way these equations operate, is actually very easy to produce. It's the detail that's more of a challenge, and we actually produce a risk certificate. We'll tell you what the comparison is, what event, what return period event would take you outside the elastic limit, for instance. That can be expressed as percentage of MBS, if that's what you want. But that event, for instance, we're looking at a building alongside the Hudson River in New Jersey, and there's been subsidence. What's the return period? What's the wind speed that would cause damage? Well, the code, SE7, says 100 miles an hour. We found 68 miles an hour would be the winds. 2/3. That's a really big difference. And that's only on part of the structure. For the rest of the structure, it's okay. But the place where the subsidence has occurred, calculated that there it is, 68 miles an hour. So we can go directly to what the risk is that you're running. And then your clients can say to you, well, what do I do under those circumstances? And you can go back to them and say, well, we're running this extra risk. You've got to decide what risk you're prepared to take. You've got to comply with the codes of practice, so you can bring it up to that, just up to that. But it's your choice about the risk. You can have as little risk as you're prepared to pay for. We have not got instances of before and after an earthquake. We have got instances before and after explosions occurring, severe damage, and in the eastern US where we are, with severe damage to a structure caused by cyclones. And that, in that area, is where domestic house owners are particularly interested, particularly in the insurance requirements. And the reason they're interested is that supposing another hurricane comes along like Hurricane Sandy. Actually, Sandy, big event though it was, the major problem was actually the rise in sea level. And so there was water damage to a lot of places. The wind speeds weren't particularly high. Just continuous over a long time, and the flooding lasted for a long time. Now we've got damaged structures, we've got the foundations washed out, and now what's the risk with another hurricane coming through? And domestic owners are very interested in that. We've talked to insurance agents in the US, and they are very interested in that as well. But what's happening is that the owners themselves want to know what sort of risk they're running. Whether as a group they'll go back to the insurance agents and say, okay, we've got this risk certificate, and we do provide them with a certificate of risk. And then at the bottom it says if there are any particular failure modes or deficits that we can see. So armed with that, they ought to be able to go back and negotiate a reduction in premium. Whether that's going to happen or not, I don't know. You tell me. We work together. And that's where it works really well. You may well already have a finite element model, and you don't know whether it's calibrated or not. We've had that on the High Line in Western Manhattan. They used to have this thing where they had passenger goods trains coming through on this thing. Made a hell of a noise. But then you've got them one story up, they come into a building, they turn locomotives around and send them off again. So we looked at that particular building. It's extremely strong, washed out by Sandy. And so what we've done there is to advise about the risk that's associated with operating that structure under normal circumstances. And I should complete that by saying we worked with the people who were wanting to change the use of that building. They had a finite element model. We calibrated it, and we told them where the weaknesses were, how to change that. And then they worked by themselves. In fact, we've done that in several different instances. Calibrate a finite element model where a consultant is then using that to play what-if games. You know, the what-if games are, can I use it for this? Can I alter the usage of it? Can I put extra loads in different places? So that calibrated mathematical model of one form or another is incredibly powerful. But unless you calibrate it, you could be a long way off. And that sort of stops your options. Because if you've got a wide confidence interval on what you're predicting, then you're not likely to chance your arm. Whereas if you know really well, then you'll say, yes, I'm certain of this. We had a railway operator in Boston, and we looked at the response of a commuter bridge, and it was sinking on one side. So we clearly saw this, went back to them and said, we've calibrated the finite element model. We looked at this. We think you've got about a month before you're going to have a serious problem. So they closed down one line, had commuters just going over one of the lines while they did the repairs. We looked at the calibration of the finite element model with what we were measuring. It was a long way off. It was a very long way off. So they were actually considering that they were okay. And as soon as the measurements went in, we saw this gradual progression. So there was sinking into the river there. So that was another one of those where we make a call. It's very easy to make the call because the information is so very clear.